This is Vedant Agrawal,
And this is Aniket Prakala.
and we are presenting a low current sensor using transimpedance amplifiers. The motivation, which is the problem at hand, so appliances such as gas sensors have very low currents flowing through them, approximately of the order of micro or nano amperes. Uh, but the thing is that normal current sensors, they read currents in the order of uh, simple amperes or milliamperes, but since sensors have currents of micro or nano ranges, our attempt is to be able to detect and display that amount of current through our sensor. So our basic idea is having the current flow through our impedance amplifier, which converts the current into a voltage. Voltage being from 0 to 12 volts. This voltage we pass through an Arduino for it to calculate the current, and we have the current displayed on our LCD screen. We have researched and read a couple of papers, and we have come up with few possible initial implementations. One way is just by using a simple resistor, that is passing a small current through the resistor and getting the amount of voltage that comes from it. The problem with this is that it has a high impedance, which negatively affects the previous circuit which is connected to our sensor, and it wouldn't be able to take such high loads. Another method we can use are magnetic Hall sensors. The best thing about these sensors is that they're not even connected to our circuit. They're basically they sense magnetic fields. So when you have a current passing close to it, it produces a magnetic field which it senses and gives us the current flowing. Only problem being is that it does not work for our specific uh, specs, which is for low currents. The idea we found was the most suitable for our project was using a transimpedance amplifier, which removes the impedance problem like we had in the simple resistor solution, and we can use it to amplify the smaller voltages that we get to larger voltages and get our output current. Here are a few papers and references we have used. This is our first implementation model. It consists of a negative feedback amplifier which has the input as a current which passes through a resistor, in this case given as R4, and that at point R4 we get a small voltage which is then amplified by the negative feedback amplifier to give an output at A. The range of our output will be from -12 to 12 volts, as we have given that as our power to the op amp. Following is the DC analysis that we have done. So as stated before, the current passes through resistor R4 to give a voltage V2. The amplifier amplifies this voltage V2 to give us VA using the formula 1 plus R5 by R2. After that, from the characteristic equation that we obtain, the slope we derive is R4 times 1 plus R5 by R2, and the max current that we can output is the max voltage divided by the slope of our characteristic equation, in this case our max voltage being 12 volts. Following are the results of the DC current input from our simulations. Uh, as we can see from the picture above, is uh, that the characteristic equation for one specific resistor value is shown here. The image below shows for many different resistor values. As we can see in this box of our simulation, the slope matches with the slope from the formula of our previous slide. Uh, this is the explanation of the pictures from our previous slide. The bottom graph, as we said, corresponds to different values of R2, which is inversely proportional to the gain. And there is a trade-off that exists when we change the gain of our circuit, and that is the range increases, but the least count that we can measure from our sensor significantly reduces. So it depends on what the user requires, whether he needs a larger range or a smaller range but more precision.
Right. So this is the result from the initial AC input that we had, and you can see for different varying gains that we have a varying output, which goes from a square wave to a sine wave for our given input because of the threshold of our input being plus or minus 12 volts, our output being plus or minus 12 volts. And this just shows that for varying values of AC and varying values of input current, we can choose our levels of precision and which our gain works best for our current input. And this also shows the lack of deformity of shape for various gain stages from various AC inputs. Now, the results from AC frequency shows that the gain actually decreases quite a bit as we go from lower frequency to higher frequency. And this would not be a problem given our slope equation and that we can calculate the exact value of gain that we have. But should we not know the value of gain given as input, the AC slope given as input, we would have a very tough time to find out the accurate measure of current that we're sensing. And to combat this, this is the challenge we initial setup, and to combat it, we introduced a variance of the capacitor over here, C, so that comes out to be a much more stable from 10 hertz to 10 kilohertz range at least, due to an increase in gain as our AC value increases because of a increase in the the resistance over the capacitor over the op amp. And we have chosen these 5 stages of gain, these 5 values of RC, which correspond to each other, to produce these lines, green, blue, red, respectively. And a few features that we've implemented in our circuit include a potentiometer so that we can give the frequency analogously to the Arduino so that we can calculate the exact gain value and get the precision of the AC current. And we can switch between AC and DC analysis to eliminate any 50 Hz noise that is usually seen or any other kind of AC noise by introducing an RC filter and choosing a different output. And multiple RC combinations have been given for the previously stated reasons of different values of gain for different values of input current so as to increase our precision. And an LCD display displays the current and the IMAX values for ease of the user, and it matches quite accurately to the output on the DSM. And this has a relative accuracy in the 0 to 10 kilohertz range, even if you don't have the exact frequency due to the stable gain that I've previously mentioned. Here are the AC equations and code that we've utilized to run all these calculations to get this AC output. And this is also the code that we've put into the Arduino so as to calculate the current based on our voltage input, which we've gotten from the output of our entire setup. Okay. So here we basically shorted the pins between the op amps. We take the voltage at the positive pin as the IR value, and we through the three equations similar to that used in DC, except now we include the omega JC value from the capacitor. We derive this gain value, which directly maps our voltage output to our current input. And these are the various frequency responses we've seen through hardware, with switches 1, 2, 3, and 4, corresponding to the resistance values you see on screen. And you can see that the gain is also pretty stable in hardware as well, which proves our simulation to be accurate. And a few challenges that we faced were that our circuit was initially designed with a range of plus or minus 12 volts, but when we had to give it an input to the Arduino can only read up to a 5 volt range. So this forces us to cut down the maximum output to 5 volts, and this reduces the range of a sensor, but the precision remains the same. And we are not able to switch the resistor and capacitor with a single switch, which would have been more user friendly. Instead, we had to use two, which are have to be switched simultaneously, for one for resistance and one for capacitance. And for variable frequency input signals, the gain does vary. And to combat this, we must constantly detect the frequency of input currents, such as when we use a gas sensor and we don't know what the frequency of our input is. We'd have to constantly have our frequency to be more or less around what the input gain would be. And this is partly combated due to the stable gain, but it's not entirely. The constraints of this would be the region of precision. We can only measure in nanoamperes and picoamperes around 0 amperes instead of like 2 amperes plus some x picoamperes. And something that could help us with this would be to feed back whatever current we've read from our circuit negatively to the input, so that we can bring down whatever input reading we have to 0 amperes, and that way we can further measure with higher precision what are current values we're truly reading. The current range of a circuit is from 1 microampere to minus 1 microampere and has the highest precision of 125 picoampere per millivolt in the DC analysis. The Arduino has input impedance that affects the input provided from it to a circuit, but it may be fixed through buffer implementation. And the precision of our op amp has an input bias current, which might be the most important thing. We cannot use just about any op amp. We have to use a high precision op amp. We have used op27 because it was available in the lab, but I think 8549 is a much better op amp to use in this regard because it has a lower bias current. This one has a bias current of 10 nanoamperes, which is well beyond the few picoamperes that we attempt to measure and might cause problems in our circuit. Now this is just comparisons of the two op amps that I just mentioned and how 8549 is better than OP27. And this is a hardware working demo that you may see at your leisure.
So what is that?
Thank you. And this is a final correct.